Advanced Technologies of Quantum Key Distribution. This course is brought to you by Gilad James Mystery School. Learn more at giladjames.com. Introduction. Quantum cryptography, specifically QKD, has been built based on physical concepts associated with quantum mechanics. In contrast to conventional cryptography, whose security is based on the complex computational and mathematical algorithms for security, it is founded on the uncertainty relations, Bell's inequalities, entanglement or non-locality. The implementation of QKD consists of detectors, repeaters, quantum memories and decoy states. These concepts form the basis of security proofs. In order for Eve to obtain the secret key, she needs to break the laws of physics, but this is impossible without her presence being detected. Since there is great need for security in a communication system, it is necessary to investigate security proofs for QKD systems. Regardless of the challenges that come with developing unconditional security proofs, a lot of progress has been realized in the last 2 decades. An unconditional security proof considers all kinds of attacks that Eve can perform, and incorporating this into the security proof is a difficult task. However, a new technique for analyzing collective attacks due to an eavesdropper was developed in 1995 by Yao. Later, Bennett et al. Realized that if the legitimate parties possess a reliable quantum computer, they can implement an entanglement distillation (ED) protocol to obtain a secure version of an EB key distribution. In 1998, based on this idea, Low and Chow then developed a formal security proof for the protocol. By using the ideas of Myers, Low and Chow then Shore and Preskel developed a simple proof of security for the BB84 protocol in 2000. This was followed by a proof of Byam, who was the second to show an unconditional security proof. In 1991, Byam's proof was then used by Gottsman and Preskel to prove the unconditional security proof of a continuous variable protocol where Alice's signals are sufficiently squeezed. In the same spirit, Inamori et al. Showed the unconditional security proof of BB84 protocol where Alice's source emits weak coherent states and Bob's detector remains uncharacterized. However, a complete security proof that is secure against arbitrary attacks by the eavesdropper and full realistic implementation of the QKD protocol remains missing. But this progress depicts that major achievements have been made in this field to prove that protocols used in quantum communication are secure for sending messages. Amongst different approaches to security proofs, a number of publications on composable security, the Finetti's theorem, post-selection technique and recently the finite length key analysis are now available. Regardless of enormous progress that has been made in QKD, there are still some theoretical and experimental problems of communicating in absolute secrecy in the presence of an eavesdropper. In particular, matching the theoretical security proofs to real devices still remains unknown. The security proofs still contain assumptions concerning the behavior of devices used by the communicating parties. As a result of this mismatch, an eavesdropper can learn part of the key shared by Alice and Bob, thus rendering some schemes insecure over large distances. Moreover, the existing security proofs have been derived in the asymptotic limit, which is not very realistic. In fact, the bits which are processed in QKD are necessarily of finite length. Therefore, thanks to Valerio and Renner for introducing the general framework for the security analysis of QKD with finite resources. The security study is mainly based on the framework introduced by Devad Winter, Cesar Corner and Renner Security. For a detailed overview of QKD, we refer the reader to